Welcome to this EWRB Electrical Service Technician Training course. I'm Aria, an electrical tutor working with Whitroy. In this course, I'll guide you through all the topics covered in the EWRB Electrical Service Technician Exam Teaching Guidelines. Today, we're starting with Topic 8.1, Basic Electrical Theory, the foundation of everything you'll learn as an electrical apprentice. Before we can safely connect, test, or repair any appliance, we must understand how electricity behaves, how it flows, how it's controlled, and how it's converted into useful work. 1. Elements of an electric circuit. First, let's look at what makes up a simple electric circuit. A circuit is a complete path that allows electric current to flow from a source, through conductors, to a load, and back again. The source can be a battery, a generator, or the AC mains supply. It provides the electromotive force, we call it voltage, that pushes current around the circuit. The conductors are usually copper wires that carry the current. In New Zealand, we have the active or phase conductor, the neutral conductor, and sometimes an earth conductor for safety. Next, we have insulation, the non-conductive material around the wires that prevents current from leaking or short-circuiting. Typical insulators include plastic, rubber, or PVC. We also have control devices like switches, thermostats, or energy regulators. They let us turn the current on and off, or adjust how much power flows to the load. Then there are protection devices, such as fuses or circuit breakers, which open the circuit if something goes wrong, like an overload or a short circuit. We may also include metering instruments, such as voltmeters, ammeters, and watt-hour meters. These measure how much voltage, current, or energy the circuit uses. And finally, the load, that's the part doing the useful work, like a heater element, a motor, or a lamp. So remember, every electrical circuit has these 7 main parts: source, conductors, insulation, control, protection, metering, and load. 2. How energy changes form. Electricity itself isn't something we can see directly, we observe what it does. When current flows, electrical energy is converted into other forms: heat, light, mechanical motion, or chemical change. For example, in a heater element, electricity becomes heat energy. In a light bulb, it becomes light and heat. In a motor, it's turned into mechanical rotation. In a battery charger, it may cause a chemical reaction that restores battery charge. Understanding these energy conversions helps us choose the right components for each job. Topic C. Ohm's law, resistivity, and measuring methods. Ohm's law tells us how voltage, current, and resistance relate to one another. We say it out loud like this: voltage equals current times resistance, or V equals I times R. If we need to find current, we say current equals voltage divided by resistance. If we need to find resistance, we say resistance equals voltage divided by current. The unit for voltage is the volt, for current is the ampere, and for resistance is the ohm. Resistance means how much a material opposes current flow. Materials like copper have low resistivity, while rubber and glass have very high resistivity. That's why copper is used for conductors and rubber or plastic is used for insulation. When we test circuits, we use different instruments. A voltmeter connects in parallel across a component to measure voltage. An ammeter connects in series to measure current. And an ohm meter measures resistance, but only when the circuit is isolated and safe. Always choose the correct range and use the prove, test, prove method to confirm your meter is working properly. Now that we understand voltage, current, and resistance, let's find out where electricity actually comes from. Topic D. How electrical energy is produced. Electrical energy can come from many sources. In a hydroelectric station, falling water spins a turbine connected to a generator. That converts mechanical energy into electrical energy. In a battery, chemical reactions create electrical potential, that's chemical energy turning into electrical energy. Solar panels convert light energy from the sun into electricity. Thermal or steam stations use heat to make steam that drives turbines. In every case, some other form of energy is converted into electrical energy that we can then use in homes, factories, or appliances. Understanding this helps us see electricity as a process, not just something that appears from a wall socket. Once we have electricity available, we need to connect it safely through a circuit. So next, let's look at how a simple circuit operates. Topic E. Operation of a simple practical circuit. Imagine a simple setup, a battery, a switch, and a lamp. When the switch is closed, the path is complete. Current flows from the positive terminal of the battery, through the switch, through the lamp, and back to the negative terminal. The lamp lights because current is flowing. If the switch is opened, the path is broken and the lamp goes out. Here we can identify the parts. The EMF source is the battery, the conductors are the wires, the control is the switch, and the load is the lamp. Every more complex circuit, a washing machine motor, a heater, or a control panel, still follows this same principle, a complete loop from source to load and back again. Now that we know how the current flows, let's practice using our formulas to calculate what's happening inside that circuit. Topic F. Determining resistance, voltage, and power. Let's use a quick example. Suppose a heater operates on 230 volts and draws 5 amperes of current. The resistance can be found by dividing voltage by current. 230 divided by 5 equals 46 ohms. To find power, we multiply voltage by current. 230 times 5 equals 1150 watts, or 1.15 kilowatts. If that heater ran for 1 hour, it would use 1.15 kilowatt hours of energy. That's the same unit that appears on your power bill. When measuring, always use your instruments correctly. Remember, voltmeter in parallel, ammeter in series, and isolate before using the ohmmeter. Working safely with test instruments is part of every question in the EST exam and every job you'll do in the field. So far we've talked mostly about direct current, where the current flows in one direction. But in New Zealand, our main supply is alternating current, so let's explore what changes there. Topic G. Understanding impedance in an AC circuit. In an AC circuit, the current reverses direction 50 times each second. That's a frequency of 50 Hz. Because the current is constantly changing, it faces not only resistance but also effects called reactance from inductors and capacitors. When we combine resistance and reactance together, we get impedance, spoken as Z. Impedance is the total opposition to current flow in an AC circuit. It's still measured in ohms, but it takes into account both the resistive and reactive parts. So, in AC circuits we use the same basic relationship as Ohm's law, only we call the opposition Z instead of R. Let's finish by putting that into a calculation. Topic H. Formula for impedance and simple calculation. The formula is Z equals V divided by I. If we know the supply voltage and the current, we can find impedance, or if we know the voltage and the impedance, we can find current. For example, if an appliance on a 230-volt AC supply has an impedance of 46 ohms, then current equals 230 divided by 46, which is 5 amperes. We speak it as current equals voltage divided by impedance. This is the same principle as Ohm's law, just applied to alternating current. You'll often use this when checking load currents or motor data plates during fault finding. Summary. So to wrap up topic 8.1, let's summarize what we've learned. A complete circuit has a source, conductors, insulation, control, protection, metering, and a load. Electricity can change into heat, light, motion, magnetism, or chemical energy. Ohm's law links voltage, current, and resistance, and we use measuring instruments to confirm those values safely. Electrical energy is generated from mechanical, chemical, thermal, or solar sources. Every practical circuit follows the same simple current path. We can calculate resistance, voltage, and power using formulas. And in AC circuits, the total opposition is called impedance, represented by Z, with the formula Z equals V divided by I. Understanding these fundamentals is essential before moving into the next topic on electrical circuits, where we'll look more closely at series and parallel connections and how they behave under load. That concludes Topic 8.1, Basic Electrical Theory. In our next lesson, we'll move on to Topic 8.2 Electrical Circuits, at the different types of circuits, series, parallel, and a combination of both.